The real number system, a visual journey. Numbers are objects we've used since childhood, counting, adding, dividing. But defining what they actually are proves more complex than it appears. Numbers are not physical marks or arbitrary symbols. They represent relationships and behaviors. They form the language through which mathematical reality expresses itself. This presentation builds the real number system from 10 foundational axioms. Each property derives logically from these axioms, creating a complete mathematical structure. The real number system will emerge not as memorized facts, but as a constructed framework with observable properties. We begin with R, the set of real numbers. Rather than defining what real numbers are intrinsically, we specify how they behave. This approach mirrors how physics treats fundamental forces. Gravity is understood through its effects, not its essence. 10 axioms govern the real numbers. 5 establish arithmetic operations. 4 establish ordering. 1 establishes completeness, the property that distinguishes real numbers from rational numbers. The first axiom states that addition and multiplication are commutative. Adding 3 and 5 yields 8. Adding 5 and 3 yields the same result. Multiplying 2 and 7 gives 14, as does multiplying 7 and 2. Order of operands does not affect the outcome. The second axiom establishes associativity. When combining 3 numbers, grouping the first 2 before adding the third produces the same result as grouping the last 2 before adding the first. The sequence of operations does not alter the final value. The third axiom is the distributive law. Multiplying a sum by a number yields the same result as multiplying each term individually and then adding. If a box contains 3 apples and 5 oranges, doubling the entire collection gives 16 pieces of fruit, the same result obtained by doubling each group separately and combining them. The fourth axiom guarantees subtraction. For any 2 real numbers, a third number exists representing their difference. When a number is subtracted from itself, the result is always 0. 0 represents balance, the unique element that, when added to any number, leaves that number unchanged. The fifth axiom guarantees division, with one exception. For any 2 numbers where the divisor is non-zero, division is always possible. Division by 0 is undefined because it asks how many times 0 fits into a given quantity, a question without meaningful answer. When any non-zero number divides itself, the result is 1. 1 is the multiplicative identity, the unique element that leaves any number unchanged when used as a multiplier. These 5 axioms define what mathematicians call a field. Any mathematical structure satisfying these properties qualifies as a field. The real numbers form a field, but they possess additional structure. The next 4 axioms establish order. Without ordering, numbers would exist without relative magnitude or position. The order axioms organize real numbers along a line. The sixth axiom states that for any 2 numbers, exactly one relationship holds: equality, less than, or greater than. Every pair of real numbers has a definite relationship. No ambiguity exists. The seventh axiom states that inequalities are preserved under addition. If one number is smaller than another, shifting both by the same amount maintains the inequality. The relative ordering remains constant. The eighth axiom states that multiplying 2 positive numbers yields a positive result. Multiplication preserves the positive-negative structure of the number system. The ninth axiom establishes transitivity. If A is less than B, and B is less than C, then A is less than C. This property allows inequalities to chain together, enabling sequential comparisons across multiple values. These 9 axioms establish an ordered field. The real numbers now support arithmetic operations and magnitude comparisons. One critical property remains: completeness. Before addressing completeness, we define the integers. An inductive set contains 1, and whenever it contains a number, also contains that number plus 1. The positive integers are defined as the numbers belonging to every inductive set. This definition makes the positive integers the minimal inductive set. It contains 1, then 2, then 3, and continues indefinitely. No gaps exist between consecutive integers. This construction yields the principle of mathematical induction. If a property holds for 1, and whenever it holds for a number, it also holds for the next number, then it holds for all positive integers. The logic resembles falling dominoes. Once the first falls, all subsequent dominoes fall in sequence. Every integer greater than 1 can be factored into primes. Prime numbers are those divisible only by 1 and themselves: 2, 3, 5, 7, 11, and so on. Primes function as atomic units in number theory. The fundamental theorem of arithmetic states that every integer has exactly one prime factorization, disregarding order. The number 12 factors as 2 times 2 times 3. No other combination of primes produces 12. This uniqueness means each integer has a distinct prime structure. The proof that every integer factors into primes uses induction. The number 2 is prime. Assume every integer up to n factors into primes. If n is prime, we're done. If not, n equals c times d, where both c and d are smaller than n. By assumption, both factor into primes, so n does as well. Uniqueness of factorization requires Euclid's lemma. If a prime divides a product, it must divide at least one factor. If an integer had 2 different prime factorizations, a prime from one factorization would have to divide a prime from the other. But primes divide only themselves and 1. This contradiction establishes uniqueness. Rational numbers are quotients of integers, where the denominator is non-zero. Examples include 1/2, -7/5, and 6, which equals 6/1. The rationals are dense on the number line. Between any 2 rational numbers, infinitely many other rationals exist. Arbitrarily small intervals contain rational numbers. Despite this density, the rationals contain gaps. Consider the equation x squared equals 2. No rational number satisfies this equation. Suppose the square root of 2 were rational. Then it could be written as a over b, where a and b share no common factors. Squaring both sides gives 2 equals a squared over b squared. Rearranging, 2b squared equals a squared. This equation shows a squared is even, which means a itself is even. Let a equal 2c for some integer c. Substituting, 2b squared equals 4c squared. Dividing by 2, b squared equals 2c squared. This shows b squared is even, which means b is even. Both a and b are even, contradicting the assumption that they share no common factors. Therefore, the square root of 2 cannot be rational. A gap exists in the rational numbers where the square root of 2 should be. Similar gaps exist for the square root of 3, the square root of 5, pi, e, and infinitely many other values. The rationals are dense yet incomplete. This leads to the concept of supremum. Consider a set of numbers bounded above, a set for which some number exceeds all elements. A smallest upper bound may exist, a boundary as low as possible while still exceeding every element in the set. This smallest upper bound is the supremum. For the closed interval from 0 to 1, including both endpoints, the supremum is 1. Since 1 belongs to the set, it's also the maximum element. For the open interval from 0 to 1, excluding both endpoints, the supremum remains 1, though 1 no longer belongs to the set. No maximum element exists. The set approaches 1 arbitrarily closely without reaching it. Yet 1 remains the least upper bound. In the rational numbers, supremums don't always exist. Consider all rationals whose square is less than 2. This set is bounded above by 2, but it has no least upper bound within the rationals because the square root of 2 is irrational. The boundary required doesn't exist in the rational number system. This incompleteness necessitates the 10th axiom. Axiom 10. Every non-empty set of real numbers bounded above has a supremum. Every bounded set, without exception, has a least upper bound. No gaps exist. No boundaries are missing. This property defines completeness. The completeness axiom doesn't construct the square root of 2. It doesn't provide a formula. It guarantees existence. Somewhere on the real number line, a point exists whose square equals 2 exactly. Completeness fills all gaps in the rational numbers. The real numbers form a continuous line with no jumps, extending infinitely in both directions. 3 properties of the supremum merit attention. The approximation property. If B is the supremum of set S, then for any number A less than B, some element in S lies between A and B. If no such element existed, A would be an upper bound smaller than the supremum, a contradiction. The additive property. If set C consists of all sums formed by adding an element of A to an element of B, then the supremum of C equals the sum of the supremums of A and B. Supremums respect addition. The comparison property. If every element of S is less than or equal to every element of T, then the supremum of S is less than or equal to the supremum of T. Order relationships are preserved. These properties are tools for constructing proofs in mathematical analysis. The set of positive integers is unbounded above. No largest integer exists. Suppose integers were bounded above. By the completeness axiom, they would have a supremum, call it A. By the approximation property, some integer n satisfies. A minus 1 is less than n, which is less than or equal to A. Then n plus 1 exceeds A. Since n plus 1 is an integer, A cannot be an upper bound. This contradiction shows the integers are unbounded. This leads to the Archimedean property. For any real number, no matter how large, an integer exists that exceeds it. For any positive real number, no matter how small, an integer n exists such that 1 over n is smaller. Consider measuring astronomical distances with a standard ruler. The Archimedean property guarantees this is theoretically possible. It may require trillions of ruler lengths, but no distance is too great. No interval is too small. The unboundedness of the integers pervades the entire real line. The real number system rests on 10 axioms. From these axioms emerge arithmetic, order, integers, primes, rationals, irrationals, supremums, and completeness. The real numbers form not merely a collection of symbols, but a complete mathematical structure with well-defined properties and relationships. Every subsequent topic in analysis, limits, continuity, derivatives, integrals, builds on this foundation. The real number system provides the rigorous basis for all of mathematical analysis.